Yeah. Hi, everyone. So we will be continuing with the neuroscience sub-theme. And we have two speakers for this sub-theme. The first one is Sabria Lagoun. She's the co-founder and the CEO of Brainstorm Scientific, a hub promoting and accelerating neuroscience and neurotechnology research. The company leads multiple activities, facilitating innovation projects in neuroscience and AI. She will discuss emerging technologies interfacing the brain and various applications of AI in neurology and mental health. So welcome, Sabria. And our second speaker will be Simriti Singh, who is an undergraduate student studying at the Manipal Institute of Technology in India. She's a passionate natural language processing and artificial intelligence enthusiast to create sustainable solutions for the challenges that society faces today. She has done cutting-edge research projects for anxiety detection, sexism, and threat detection. Simriti is an upcoming data science intern at United Health Group, Optum, and a recipient of MyTech's GRI Award. And we will be starting with Sabria's talk. So welcome again, Sabria.
Thank you very much. And thanks to all of you who are coming into this session. I can see the attendees coming through. So the brain and AI, this is a very, very broad topic. But today we said that we would focus on health, although I might hint on some other applications as well. I will quickly share my screen with you. And I would say let's just go through a couple of examples of use cases for artificial intelligence applied to neurology, psychiatry, or other, motoric related brain issues. And then I will maybe go for a Q&A where we will discuss together what we could do in order to find biomarkers, use biomarkers, or perhaps even use artificial intelligence to interact with the brain. So, as you know, artificial intelligence and neuroscience have been long tied together. The reason is that the first neuroscience, the first AI algorithms were kind of experimental ways to reproduce how the brain was working. I think you might have heard of the perceptron, which is reproducing kind of the visual letter recognition. So there's quite a lot of amazing early research that was stemming from neuroscience and that created some of the first AI algorithms. Obviously, when we talk about the brain, we're talking about an organ. And like many organs, such as the liver, for example, you have a certain set of biological cells that are having a function, that are interacting with each other. But what you have to understand is that the brain is not only a mass of cells, but that is an information processing machine. Like many other organs in the body, you have different inputs and outputs, obviously. But when it comes to the brain, it's not only about the internal state and the various hormonal levels, but it's also an effector, so the way we are an agent and act on our environment. And what I want to tell you before we start looking into technical solutions is I want you to grasp the complexity of the organ that we're going to talk about. So I would suggest let's have a look at these different cells. A recent study in 2020 has shown that even in a small area, which is the motor area of the cortex of a mouse, there are so many different types of neurons that are not only genetically different, but that have different electrophysiological property. So this word, electrophysiological, means the way that the neurons connect with each other and the kind of message that they are sharing. So it can be, for example, a logical message, such as inhibition or activation, if you think of logic doors in electronics, or it can even be the threshold of activation or the density of connection, similar to an artificial neural network. And so all of this is not only determined genetically, but also the way that all these neurons are acting and responsive is linked to which neurons they are. As I told you, there are so many of them that we have not even discovered. We have not even discovered the full range of them. It's also linked to life events such as trauma, PTSD, childhood events, even childhood bonding with the parents, nutrition, obviously. Socioeconomic level has a huge impact, especially studying, so learning languages, learning facts, learning how to work with your hands on certain technical skills such as music can really, really change the brain activity and the way the brain functions. Sleep, social environment, so even the kind of diversity in your environment will change your brain activity. Life events, obviously, ecological environment. So we're talking now about various chemicals or medications or microplastics. We still don't know what it would do, but of course, various genetic backgrounds, and you don't need to have a genetic specific genetic mutation, but it could even be inherited genetic modification through epigenetics, which is the way that parents can transmit certain stress levels, certain trauma to their children. So we're talking now about a machine where we don't really know the individual components, and any sort of environmental input or genetic input or what you fuel the machine with can change the way it functions. And that's basically what I wanted to tell you before we get started on the AI topic. And I know that when we talk about AI, we talk about data. And here you can see that the number of variables and the quality of the data and the type of data is extremely complex. And obviously, we have really an explosion of parameters when it comes to this. So the first aspect is really not only the underlying matter that is making the brain work, but also the outputs and what kind of data output you might get out of the brain. Obviously, behavior, and behavior does not have to be, very metaphysical. So it's not only generous behavior or whatever. It can even be a behavior on a certain app or a certain software. Motricity is the output of the brain, obviously. Speech. You can work on biological biomarkers that I will detail a bit later. And you can have sensory differences, so how you perceive things, how you perceive color, how you perceive touch. You can have anatomy biomarkers, and of course have differences in pain and cognitive abilities. So if you think about your algorithm, you're gonna have now so many different ways to approach the brain. First of all, gathering brain data itself is very complex, but also all of the derivative biomarkers that you can derive from it are highly dependent on so many environmental factors that it's very hard to control, confounding variable and make accurate prediction, especially when it comes to healthcare. So now that I told you that it's very complicated, and I hope it was understandable how hard it is, I'm going to show you a few ways that AI is now actionably working for creating, interfacing the brain in healthcare. Obviously, now I go to this very niche of healthcare, but AI and brain research have many, many, many more common points. It can be brain-inspired AI, brain-inspired microchips. It can be swarm robotics. It can be organ on a chip. So there are so many ways that we could intertwine both. I'm only talking now about cases that would apply to healthcare, but if you're curious, we can also talk about it later. So the first aspect, of course, is diagnostics. So whether it comes to psychiatric illness or neurological illness, one of the main issues is all of this is diagnosed way too late. Obviously, for many illnesses, for example, Parkinson's disease, some of them are very, very well laid out. So You know that if you have Parkinson's disease, you have tremor, you have some problems remembering the automatic behaviors, such as tying your shoelaces or putting down your shirt, but you can remember everything about your life. So, for example, you don't forget the name of your children or anything, but unlike Alzheimer's, but you have trouble maybe doing things that motorically that you were able to do for your whole life. And the reason is because of a dopaminergic pathway that goes from a little black cells that are full of dopamine. It's called the negrostriatal pathway. You don't need to remember this, but for some of these illnesses, you know exactly what's going on. And you can even see on this brain, without any sort of staining or biological modification, you can just cut the brain and see, look, this is a healthy patient on the left and a Parkinson's patient on the right. And what happened is these cells, they just died. So, you know, this is a very clear biological reason for this. And in this case, obviously, the main issue is accessing the brain. And so whenever you are trying to understand neurological illnesses or understand psychiatric illnesses, most of the times the first symptoms are coming from a patient's complaint. It's not that you can suddenly make a test and think, oh, you might have this or that in the background. And because the brain is so plastic and always recovering itself and always finding adaptive mechanisms, whenever there is an issue that the patient is complaining about, for example, oh, I have problems remembering how to do things with my hands, or I'm shaking a bit, then it's usually quite advanced. And so one of the main promises of artificial intelligence is then for two aspects. One of them is early symptom detection, helping the accuracy of diagnostics, and helping decision making. So obviously, I'm going to show you ways that AI is enhancing existing mechanisms, and then I'm going to show you how it can disrupt existing mechanisms. So this is for the enhancement part. There are a couple of papers. You can have my slides afterwards if you want to, that are showing different methods. And I just wanted to show you some recent ones published in Nature. The first one is EEG signal, which is measuring the electrical activity on the scalp of the brain. And there, this is a paper around how to train deep learning algorithms if you do not have labeled data. So the main bottleneck of such diagnostics or detection of seizures is typically that the data you need to arrive to certain diagnostic is very high, and the expertise, so the labeling of data, is the bottleneck. But I think if you know about AI, you know this is mostly the problem for deep learning. And now there are a couple of approaches now focused on weak labels, so not on high-level clinicians, but on really people that don't have a high level of precision, 40% precision levels. And then they're using this method in order to reduce the costs and increase the speed of making algorithms work. And I just thought it was maybe an interesting topic of weak labeling applied to such a complex healthcare topic. The second aspect is obviously for stroke decisions. So, you know, when someone is presenting some symptoms, even sometimes subtle, they might be having a stroke or a microstroke, and making a decision to, you know, go into the OR or what is going on is quite tricky, and so there's always a question of time. So here you can use, of course, more image processing algorithms in order to help the operators of the brain scans understanding what is going on without having to wait for the doctor to be available and interpret the results. So we have here two examples that are kind of just highly enhancing the speed and cost and decision-making flow of the decision making in terms of what is going on in the brain. The issue is here we're talking about people that are already struggling with symptoms or that are really on the verge of death. And this is the same for many aspects of the brain. The access to early biomarkers is really the main bottleneck. And so you can catch up on a lot of things regarding, for example, the liver or the kidney if you do your routine yearly checkup. But it's very hard to really have early biomarkers that you could use and predict risk scores with, because brain genetics are messy and because brain activity is always tricky. So the latest trend, and I think you will hear more of this today, is to really use seamless data collection for early diagnostics. And two examples are voice biomarkers, so speech for early diagnostics of mild cognitive impairment or of psychotic or depressive episodes. There are a few pilot projects on this and a few publications. And another one is for tremor, for tonico-clonic tension, for two examples of illnesses, Parkinson's disease or multiple sclerosis, using accelerometers and various biomarkers of wearables such as Fitbit, especially as they are also measuring heart rate, so you can really do some comparative and more big data driven studies, because so many people have these tools already at home, so you don't need to schedule an appointment with a neurologist, and you're really able to do a lot of studies with this. I think this is not new to you. I'm gonna, so the number one topic is how to find new and non-invasive biomarkers, because doing a brain biopsy is always a bit more tricky than doing a skin biopsy. So it's much harder to like drill into your brain and see what's going on. And so this is kind of what we are aiming to do, using kind of more real-life evidence AI gathering. The second topic that I wanted to mention is treatment. So, of course, artificial intelligence can be used for drug discovery and for pharmacology, not only through analyzing brain activity or analyzing the various symptoms and trying to recommend a specific drug based on it, but also through a bit more advanced topics, for example, brain on a chip, which are electronic constructs that are reproducing the brain of certain individuals, and even making mini brains. So you would take part of the skin of a patient, transform it into a stem cell, and then put a cocktail of drugs on top that would transform it into neurons. And so you would have neurons that would look genetically and act genetically like your brain, your own brain neurons. And then you can do this high throughput that is impossible to do by eye, but basically test every type of drug that exists with every type of situation, and then use artificial intelligence to really predict how the output would be, especially the more you get patients and the more you can predict. I'm sure you know this guy. He's been putting a lot of extremely bold claims out there through his new product called Neuralink, which is a brain-computer interface implants. And obviously, brain-computer interface is not new. So this topic has been existing, and many patients have brain implants already. Most of the patients are Parkinson's disease patients, as I mentioned already. One of the main treatments for Parkinson's disease is stimulation. So you would basically replace these little black neurons that were lost by a little electrode that sends electrical current, so that, you know, whatever fibers were still there can still get the juice and continue transmitting. And a lot of people have brain implants on this. What Elon Musk is trying to achieve, and what has been into research for decades already, is to record the brain activity, pre-process it, and then decode it in a way that you find a way to interact with the computer in a very clear way. And this has been really booming and enabled mostly through the rise of artificial intelligence, because it's much easier to make predictive algorithms than to have a very, logical software. logic-based software. So here, I'm going to show you an example of what was already achieved in the research settings. In 2019, some researchers have been recording the brain activity only in the surface of locked-in patients who are not able to move, not even their mouth. I'm sorry. And they have been showing, they have been asking them questions, and I'm sorry, and predicting the answer on various patients that were implanted. And I'm going to show you how it looks like. I hope that you will be able to hear my sound. This is on the left. This is the brain model that was implanted. Sorry, I'm going to go back to the beginning. This is a brain model that was implanted with a probe. It's a surface probe with a bunch of electrodes. And on the left, you have what actually happened, the question that was asked. I'm sorry, my Wi-Fi is really bad. And on the right, you have what the AI was predicting. Okay, this is not working. Okay, there you go. So the participant hears a question, and this is what the question is decoded from the brain activity. So the AI is able to not only decode what the patient was perceiving, but also what the patient was answering based on their brain activity. I'm very sorry. This is a little bit buggy. Maybe I should...
Which musical instrument do you dislike hearing?
Yeah, the bandwidth is too bad. Give me a second.
None of these.
From
There you go.
0 to 10, how comfortable are you?
6.
How is your room currently?
Fine.
From 0 to 10, how comfortable are you?
4.
So you can see, I mean, I had to decrease the bandwidth, so maybe you didn't see the pixels correctly. But what I wanted to say is that it is quite interesting that significantly, with a big significance, this algorithm is able to predict the thought. It's not really the thought per se. It has been trained, obviously, but it's quite interesting, this encoding and decoding of language already exists. It's already out there. So there is some scientific basics for the Elon Musk project to work, obviously. But we have to discuss a lot of different ethics questions and so on. But the next logical step of this technology is then, are we able to, sorry, now we have a music. Are we able to maybe go the next step and then replace brain areas that are damaged? For Alzheimer's disease, for example, the hippocampus is typically damaged. And since the early 2000s, there are projects to create a chip that would be kind of a brain prosthesis. Now, the last point is management, and I want to keep it open for you. There is one of the main issues if you're dealing with patients that have psychiatric or neurological issues is their cooperation and their self-monitoring might be difficult, especially when their cognitive ability are impaired, if they're undergoing psychosis or depression, or if they have memory problems. So the number one bottleneck is to find biomarkers that people don't have to input themselves, and that are able to be accurate enough to send an alert and to be able to be monitored. Some examples are exacerbation for psychosis through various startups and topics that are being held in order to understand basically what could be happening in this person's life. Are they manic? Are they sleeping enough? And this kind of biomarkers are the ones important for management. I'm going to leave it here because I don't want this to be a long monologue, but rather of a discussion. If you want to hear more about us, this is our website, thebrainstorms.io. We are a big gang of neuroscientists, biologists, but also AI specialists, robotics experts. And we work not only through scientific communication, as you saw today, but also we are working on innovation projects, and we work in a way that anyone can join in, and if they have an idea, we can try to help find funding for it. So if you're curious about this topic, if you want to write, if you want to just talk to us, don't hesitate. We have a contact form, and you can register to our newsletter, so you can really head out to our website and have a look. And I'm going to close this tab and come back to the Q&A.
Thank you very much, Sabria. It was a great presentation. I first want to mention how beautiful your visuals were. Also, we were really impressed. And our first question is on the QA, do you know what are the underlying causes of degeneration of substantia nigra? Is there a way to prevent this premature degeneration?
Yeah, so this is just the Parkinson example, but there are a lot of different neurodegenerative diseases. Obviously, it's always multifactorial. For Parkinson's, there are some genetic factors for certain ones. And it's just very complicated. So some of them are genetically inherited, and some of them are idiopathic. So it means it just starts. But we know for prevention, we know that there are multiple factors that are preventing symptoms to appear. So, the brain is extremely plastic, and the brain is able to reorganize itself and also to generate new neurons quite a lot. Although this was debated for a long time, but now we know that it's possible to happen. A lot of meta-analytical studies have shown that there are neuroprotective factors. So sports, nutrition, level of socioeconomic background, obviously, and level of studies, multilingualism, practicing an instrument. So anything that is really brain stimulating is preventing you, most of the times delaying up to 10, 15 years the onset of symptoms. But also for some people, you will look after their death that they have quite a damaged brain, but they never had cognitive complaints. So it's still, correlation and causality is a big problem. So I don't want to make crazy claims here that if you eat blueberries every day, then you will never have Alzheimer's. But definitely, it is known that sports nutrition, everything is helping. And when it comes to various neurodegenerative diseases, there are some clinical trials around detecting it early and taking medication that would stabilize it at an early stage, but it's still a big topic. Yeah,
thank you very much. I have two questions myself as well. I wanted to ask you, with regards to the biomarkers you presented, you're referring to, I think, the EEG and fMRI scans, correct?
Mm-hmm.
Okay, then how often are AI-powered solutions deployed in practice right now?
So for the data analysis, like for the more basic data analysis, I think nuggets of AI are being included. I'm going to take a step back and talk about healthcare in general now. Obviously, AI-powered diagnostics are always an issue. Not only because it's hard to apply statistical studies to the individual level, because you use a group to see could you predict compared to a control group, but then on a single level person it's always difficult. And also there's a liability. So now we have to really take a step back from the technical issue and discuss the liability issue, which means that in the end the doctor is still legally responsible to make the diagnostics. And this is something that is also joining a bit of resistance on this end. In terms of diagnostics, the best way to do it at the moment is to have this kind of two sets of eyes, and this is very used in oncology. Oncology is very, very, very good with detection of tumor, but brain tumor is not the main problem it is a big problem in neurology, but it's not the main concern, of statistically,
Okay, thank you very much. Thank you very much for your great presentation. I think it was really interesting. Thank you. And
thanks a lot for the invitation, and to all of you. I'm on LinkedIn, so you can add me, obviously, or check out our website if you have any questions. And have a great day.
Thank you. You too.
Bye-bye.